Welcome to the videos about implicit differentiation. Let's talk about where the term implicit comes from. We know differentiation now very well. It's just taking the derivative. But in order to understand implicit, I think we better talk about the definition of explicit functions. An explicit function is one that can be described by expressing one variable completely and totally in terms of another variable. These are functions we're familiar with. There is y equals some manipulation on x. Here is y equals some manipulation on x. It is explicitly given to us the direct relationship between there we go, x and y. Okay, that is an explicit function. Well, what if we have still a relationship between x and y, but we can't express it explicitly? In other words, algebraically, we can't do all the algebra steps and get one variable completely by itself on one side of the equal sign and the other variable totally by itself on the other side of the equal sign. So as long as we can solve an equation for y and express y completely in terms of x, we can use what we know about differentiation on these functions. We learned lots of rules: product rule, quotient rule, chain rule, all kinds of rules in order to be able to find the derivative. However, how do we find the derivative of a function that shows a relationship between x and y that's not this explicitly defined? Let's say that there is an implied relationship between the two variables, and implied is where the word implicit comes from. Algebraically, at this point in my math career, I cannot solve that and put y completely in terms of some manipulation on x. There is not an explicit relationship here, but there is an implied relationship between x and y. Now, which is the independent variable and which is the dependent variable? I don't know. I'm going to have some more clues. But there is an implied relationship between these two. How do I go about finding the derivative of that with respect to x? There's no x there. I know how to find the derivative of that term. How do I find the derivative of a product, x times y? So when there is an implied relationship like this, I have to use something called implicit differentiation. So if I have implicit functions, some functions are defined in a way that makes it extremely difficult to find the derivative of one variable with respect to the other. But in implicit functions, we still have an independent and dependent variable. I'm just going to have some sort of clue that tells me which is which. Well, let me ask you this. What does this mean? If you give me this function and you say find dy dx, did you just tell me which was the independent and which was the dependent? What if you told me to find dx dy? You just told me which was the independent and which was the dependent variable. With respect to is the independent, and in the numerator is the dependent. And so if you can tell me which of those there are, then I'll know how to go about implicitly differentiating this function. Now, let's go back to explicit. With explicit, when I have y given as some manipulation on x, I'm guaranteed, in the functions we work with anyway, in elementary functions, that we have a function. There are some subtleties, we'd have to look for, but most of the time I'm dealing with a function. In other words, one x value yields me one unique y value. I pass the vertical line test with most explicit functions, most elementary explicit functions. Well, clearly, which this is the graph of this implicit function, clearly I don't pass the vertical line test. So how do I even know I'm talking about a function? Calculus is mathematics of functions. Well, I can talk about different pieces of this function. Let's say there's this piece. That passes the vertical line test. Let's say I keep going all the way up to here. Well, that green chunk right there is going to pass the vertical line test. So if I limit my domain and just talk about the values that will give me that part of this graph, of this function, then I'm dealing with a function. What about from here to here? I'm perfectly fine. That passes my vertical line test. What about from here to here? Again, I passed the vertical line test on that chunk. So if I'll break my domain up into pieces of this implicit relationship, if I look at just those smaller pieces, I'm guaranteed to have a function. And with a function comes derivatives. So let's talk about implicitly differentiating. This, by the way, is known as the folium of Descartes for the math nerds in the room. So we can use the method of implicit differentiation to find the derivative of this function. And we are going to see functions that look a lot like this, and we're going to be asked to find dy dx. We're going to be asked to find the derivative of this function, y, with respect to x, which tells me that I'm differentiating with respect to x. X is the independent variable in the driver's seat. So we find an implicit differentiation. We differentiate both sides of the equation with respect to x, and then we're going to equate the results. So this process, and again, I'm all about processes. Learning math and applying math steps is a process. So if you'll learn the process and apply the process no matter what the function looks like, you'll always get the right answer. So here is our function. Since y is assumed to be some function of x, we're going to find dy dx. And we're going to work with the power of that symbol right there. If this is a true statement, if it's true that the x value cubed plus the corresponding y value cubed must equal 6 times the x value times the y value, then no matter what mathematics I do, as long as I do the same mathematics on both sides of this symbol, then what's left must be equal as well. So the integrity of the equal sign is what allows us to walk through our process of implicit differentiation. So they're the same function on both sides as long as I do the same mathematics on both sides. For instance, if I multiplied 2 on the left and multiplied 2 on the right, that result would be equal. If I took the natural log of what was on the left and took the natural log of what was on the right, then the result would be equal. So all I'm doing here is the derivative. I'm going to take the derivative of what's going on the left side of the equal sign, and it has to be equal to the derivative of what's going on the right-hand side of the equal sign. So I'm going to differentiate term by term. Term by term. I'm taking one term at a time. So let's look at this term. Well, the derivative of that term with respect to x is just the power rule. The 3 pops down front, reduce the power by 1. Now, the derivative of this next term, y cubed, is a little bit different because, again, I have y that is some manipulation on x, and I have all that cubed. This is a chain rule problem. I got to use the chain rule on this term because this function has been put into that function machine, and that whole thing has been put into another function machine. This is a chain rule problem. So the chain rule says the derivative of the outside, which is a power rule, not changing the inside. Well, what's inside that function is y, and that's this function right here, times the derivative of what's inside. Well, what's inside is x, right? Or some manipulation on x. I don't know that it is x. I can't say the derivative of that is 1. But I can say the derivative of that is dy dx. So that comes from the chain rule. That's the only thing here that might not be quite so intuitive in implicit differentiation, is when to use the chain rule and what that's going to look like. And now that's the derivative of the whole left-hand side. Copy down my equal sign, and now I have to have the derivative of that side. Well, that side is a product. So now I need the product rule, which is 1d2 plus 2d1, right? So let's say that 1 is 6x and that 2 is y. So 1 d2, well, what's the derivative of y with respect to x? dy dx. Plus 2 d1. Now this is still a true statement because I did the same mathematics on the left side as I did on the right side. So that is the only calculus step in this whole process of implicit differentiation. Now what did they ask us to find? They asked us to find dy dx. So all the rest of the steps are algebra steps. So the next thing I want you to do is anything that has a dy dx in it, I want you to correctly algebraically put it on the left side of the equal sign. So I have 3y squared times dy dx. That gets to stay on the left-hand side of the equal sign. I need to subtract this, so minus 6x times dy dx. And anything that does not have a dy dx in it, I want on the right-hand side of the equal sign. So I have to subtract this to get it on the right-hand side of my equal sign. This is already over on the side where I need it. Now, do you see why I did that? Because now I have gathered like terms. Both of these terms have a common factor. This is 3y squared times dx, minus 6x times, dy dx. So I'm going to factor dy dx out of both of those terms. That leaves me with a 3y squared minus 6x. That still has to equal negative 3x squared plus 6y. I'm going to divide both sides by this term so I can isolate and get dy dx on its own because this is what I'm after. So I have negative 3x squared plus 6y over 3y squared minus 6x. Now that's done. All through, all said, all done, all finished. I don't have to simplify. If this is not a multiple choice problem, I'm not going to simplify. But let's say it was. Every term has a 3 in it. So let's get rid of those 3's. We have negative x squared plus 2y over y squared minus 2x. So there's our final answer. This is the derivative of y with respect to x for this implicit function. Okay? So let's talk about steps in the process. Step 1, differentiate term by term. Make sure you recognize when to use the product rule, when to use the power rule, when to use the chain rule. Then all the rest of the steps are algebraic steps. Everything with dy dx in it, you need to algebraically correctly put it on the left-hand side of the equal sign. Everything else algebraically correctly on the right-hand side. Then factor out your dy dx, and then divide by the term that's multiplied by your dy dx, and the result will be the derivative of y with respect to x. Notice we're used to our derivatives being in x only. This derivative is in x and y. You're going to have to give me an x coordinate if you want the derivative at a certain x value. And I'm going to have to go over here and plug that value in and find the corresponding y coordinate that goes with it before I can find the slope of the tangent line at any x value. All right, so we'll stop there and we'll move on with the lesson in the next video.